Hello everyone, welcome back. In our today's video, we will be discussing group 17 elements of P block. As we know that this particular group is also known as halogen, consists of 5 elements, that is fluorine, chlorine, bromine, iodine, and astatine. In this particular video, we'll be discussing the general trends in physical and chemical properties of group 17 elements, where we'll be discussing the oxidation state, electronic configuration, the chemical trends in group 17 elements, and some other physical and chemical properties. So let us start the discussion with the general introduction of group 17 elements. As we know that fluorine is the first member of this group, okay, group 17 or 7A. It consists of 5 elements: fluorine, chlorine, bromine, iodine, and astatine. The elements of this group are collectively called halogens. Okay, halogen is a Greek word. Okay, halo means sea salts and gene means producing. So basically, they are sea salt formers. As the first 3 members of this group are found as chlorides, bromides, and fluorides. Okay, in the sea. Astatine. Okay, the last element of this particular group is radioactive, and very less study has been done till date on astatine. Coming for the electronic configuration, this is how we can write the electronic configuration of this element. Fluorine has a electronic configuration of 1s2 2s2 2p5, which can be written as He. 1s2 is helium configuration, so we can write He in a brief. Chlorine is 1s2 2s2 2p6, 3s2 3p5. So 1s2 2s2 2p6, which is the configuration of neon, we can write in brief as Ne 3s2 3p5. Similarly, we can go for bromine, iodine, and astatine by writing in brief way by using the noble gas configuration. Their atomic number, if you see, can be easily generated by adding 9 plus 8, 17, 17 plus 18, 35, 35 plus 18, 53, and 53 plus 32, 85. As I have mentioned in my previous video also, you can add 8, 18, 18, and 32. That is how we can generate the atomic numbers in a very simple way. And if you see the configuration of this particular element, the last shell will always have S2 and P5. You can clearly see the last shell of this particular element, okay, of this group has S2 and P5, as a result of which the general configuration will be NS2 and P5. They will have 7 valence electrons, okay. And because by having 7 valence electron, they are just one less than octet, so they have a huge tendency to take one more electron and complete their octet or fully fill the p subshell. As a result, they have a very high tendency to gain electron. Okay, as a result, if you take their oxidation state, the most common oxidation state which this particular group will show is -1. Okay, they can easily gain 1 electron to complete their octet. Apart from -1, except fluorine, others shows +1, +3, +5, and +7. Okay, that can happen. They can expand their oxidation state or can increase their oxidation state because of the availability of vacant d orbital in their valence shell. But fluorine, being an element of the second period, will not have any d orbital, as I have mentioned in the previous cases, in the previous groups also, that because the element in the second period will never have any d orbital in its valence shell. Principal quantum number 2 does not have any d subshell. As a result, fluorine will never be able to expand its octet, and very important, fluorine, being the most electronegative element, can never show positive oxidation state. So it will always show negative oxidation state and will always show -1 only. Okay. Now, how the other element can show the higher oxidation state can be explained in this way. Halogen atom in the ground state has Ns2 Np5 configuration. So it has only one unpaired electron. One unpaired electron, either it can it can share it for bond formation. So if it is sharing with more electronegative element than itself, then it will lose it. So, or you will get an oxidation state of +1. If it is sharing with less electronegative element than itself, then obviously it will actually get an oxidation state of -1. Okay, so that is how actually it gets an oxidation state of +1 or -1 in its ground state. But the other oxidation state, higher oxidation state, it can do it by exciting the lower electron to the empty d orbital, which the elements other than fluorine has: chlorine, bromine, iodine. So as a result of which, what they can do is they can easily transfer 1 electron from P to D. You can see over here now it has 3 unpaired electrons. So 3 unpaired electron will account for +3 oxidation state. The second excited state, if it actually transfer one more electron or jump one more electron will jump to the higher energy state, that is the nd orbital, then it will have 5 unpaired electron. So obviously it will have an oxidation state of +5. In the third excited state, the electron can easily jump to the nd orbital and can have 7 valence electrons. So obviously it will have an oxidation state of +7. So that is how actually they can show +3, +5, and +7 oxidation state, which fluorine will not be able to show because of the absence of d orbital. Coming for the next, that is the anomalous property of fluorine. As I have already mentioned, fluorine can show only an oxidation state of -1. That also comes in its anomalous property. Now the question is why fluorine shows anomalous properties. As we have discussed for the other element, the first member of any group will always show different property than the rest of the member. It is because of its small size, first of all. Obviously fluorine is the smallest, okay, and very, very small. It is because it is present towards the extreme right, sorry, of the periodic table. So it will be very, very small. Okay, so because of its small size. Second, it is because of its high electronegativity. It is the most electronegative element. Then high ionization enthalpy, obviously smaller size leads to very, very high ionization enthalpy, no tendency to give electron only. It has low fluorine bond dissociation energy. Remember that is what we'll be talking about in our coming sessions, in our coming sections. Over there, I'll be discussing why fluorine has low bond dissociation energy. Even though it is small, the bond should be short and strong, but fluorine has a very low bond dissociation enthalpy. It breaks very easily. It is very, very reactive. Okay. And finally, it does not have any d orbital for bonding. That is what I have told you. It does not have any empty d orbital in its valence shell, as a result of which it will not be able to expand its octet as the other element does. Okay. So this is the reason why fluorine shows anomalous properties. Okay. Coming for the next, talking about the halogens. Okay. Halogens, all the halogens are colored. Okay. All of them, like fluorine is light yellow, chlorine is greenish yellow, bromine is reddish brown, and iodine is deep violet. Okay, so why they are colored? Now obviously any system, whenever it is colored, is because of the excitation of electrons. So over here also the same thing happens. The color of the halogen is due to the reason that the molecule absorb light in the visible region. Okay, they're molecules like fluorine, chlorine, bromine, or iodine, as a result of which the electrons are excited to higher energy levels. Okay, because of the absorption of the light from the visible region. And the amount of energy needed to do actually for excitation decreases progressively. Remember that it will decrease progressively from the fluorine to iodine. Okay, and consequently there will be progressive deepening of color of the halogen from fluorine to iodine. So fluorine will be light and the iodine will be very dark colored. Okay, that is deep violet. Now why it is so, why actually the energy needed of, obviously the amount of energy needed for excitation will decrease progressively. It is because of the electronegativity of the elements. Fluorine is the most electronegative element, so the lone pair which it has will be holded very tightly by the system. Okay, by F2 in the F2 molecule. So a huge amount of energy will be needed. Okay, and in the very same way, when you go for iodine, iodine has very low electronegativity, as a result of which what will happen is it will have very uh, actually the energy required to excite this electron from iodine molecule will be requiring very less energy because of its very low electronegativity. Okay, since fluorine atom requires large amount of energy for excitation of electron, as I have told you, it's because of its electronegativity, and therefore absorb violet light. Obviously violet light is the highest energy, right? If you compare the 7 colors of the visible region, then violet is the having the highest frequency or highest energy, and that's why it actually appears yellow. That is the complementary color. On the other hand, iodine requires low energy. Okay, so low energy means obviously it will absorb in the yellow light region, that is the lower energy region of the visible light. So obviously the complementary color which will be released will be deep violet. Okay, so always remember that the color which is absorbed is the complementary color, not the color which is absorbed by the system. So that is how actually we can understand that why the halogens, okay, the molecules are colored. It is because of the excitation of electrons. Okay, to different due to the higher energy levels because of the absorption of the light in the visible region. Okay, and depending upon the electronegativity, they have different colors. Okay, because different types of energy will be required for the excitation of electrons. Okay, then coming for the bond dissociation energy, as I was discussing in case of anomalous properties of fluorine. Okay, remember that the bond dissociation energy of chlorine, bromine, and iodine decreases down the group. Obviously, it's because of size. Okay, the bond dissociation energy of fluorine is, however, lower than that of chlorine and bromine, because of interelectronic repulsion present in the small atom of fluorine. Okay, fluorine is very small. Okay, exceptionally small, 2 shells and a compact 7 electrons. Okay, between 2 fluorine. So if you have a F2 molecule, what will happen is this 2 particular fluorine atom will have huge repulsion. Okay, because of which the lone pair on the fluorine and the bond pair will start repelling one another, and because of this repulsion, the bond actually breaks very easily compared to bromine and chlorine. Even though their size is bigger, even though the bond is longer, then also fluorine breaks very easily, even though it is having a very short bond. It's because of the interelectronic repulsion in fluorine atom, because of its very small size. Okay, because of which the bond order, if you see, it will be Cl2, Br2, F2, then I2. Okay, that is very rare. Okay, fluorine should have the highest bond dissociation energy because it is very short, it is very small. Okay, but because of the interelectronic repulsion, okay, there are many electron in the system, 3 lone pairs on one fluorine, 3 lone pairs on the another fluorine in F2 molecules, and since they are very close with the bond pair, so obviously there will be huge repulsion which forces it to break. Okay, that's why F2 is very reactive. Okay, even the direct fluorination of hydrocarbons with F2 is not done because it occurs explosively. That is the reason why. Okay, it is very reactive. Okay, on the other hand, when you react with chlorine and bromine, we usually use the energy in the form of heat or light. Okay, so that is the basic reason. Coming for the next, that is the trends in the chemical and the chemical reactivity. We'll be trying to take 2 chemical reaction. The first one is reactivity towards hydrogen. Okay, so how does it react towards hydrogen? They all react with hydrogen to give hydrogen halides. Okay, HX, like HF, HCl, HI, HBr. Okay, the acidic strength of this halide decreases in the order. Okay, if you see the acidic strength, then HI will be the most acidic and HF will be the least acidic. Okay, it is because of, again, the bond dissociation energy. The bond dissociation energy in HI is the least, so it breaks very easily, so it gives H plus very easily. HF, okay, the bond dissociation energy is high. Obviously it is HF, so the bond is short. Okay, it will be strong, so it will not be able to give the hydrogen ion so easily compared to HI. So it is HI first, then HBr, then HCl, and then HF. The stability of this halides, okay, if you see, it decreases in the order. It will be HF, okay, will be the most stable. Obviously, that's what I've told you. It's because of the shorter bond between hydrogen and fluorine, then little bit longer in HCl, then longer in HBr, than the longest in HI. So it breaks very easily. When it breaks easily, it can supply H plus very easily. So it becomes most acidic. So remember that hydrogen iodide is the most acidic because it is the least stable. Okay, it breaks very easily. The bond is very long. Okay, so that is how we can understand the reactivity towards hydrogen. So all of them will form hydrogen halide with hydrogen, and the the stability and the acidic nature goes as given. Coming for reactivity towards oxygen, all of them forms oxide. They form many oxides. Okay, and most of them are unstable. They are not that stable. Fluorine forms 2 oxide. Okay, that is OF2 and O2F2. Actually, these are not oxide also. They are essentially called oxygen fluorides. Okay, because fluorine is more electronegative than oxygen, so we cannot call it oxide, so we call them fluorides. So they are oxygen fluorides because of higher electronegativity of fluorine than oxygen. So basically they are not oxide, they are fluorides. Okay, they are oxygen fluorides. Chlorine, bromine, and iodine form different types of oxide, okay, which ranges from +1 to +7. So they have a long range of oxide formations. Okay, they can go from +1 oxidation state till +7 oxidation state. Okay, so there will be many different types of oxide which this particular group forms. Okay, so that is what actually all about this particular group 17 element discussion. Okay, so these are the general trends in the physical and the chemical properties of group 17. Okay, so thank you everyone. Do subscribe for this channel for explanation on various topics in chemistry. Thank you.